thank you all for staying for our last session. And the last session is, of course, the most exciting and most interesting one on innovation and technologies. And it is my great pleasure to introduce Dr. Azadeh Yazdan, who will be speaking on engineering cortical plasticity in non-human primates using optogenetics. Azadeh received, well, first of all, most importantly, she's a Washington Research Foundation Innovation Assistant Professor at the University of Washington, who received her PhD at the University of Michigan under the guidance of Daryl Kipke, and did her postdoc with multiple fellowships at UCSF with Philip Sabes. She develops and implements new tools for using optogenetics in non-human primates and rats with a focus on inducing targeted plasticity for rehabilitation. It goes without question, and maybe this is not something that everybody is aware of, that optogenetics is actually a very, very difficult technology to get to work right in non-human primates, and so I'm extremely excited to see what you have to say today. Let's welcome.
Thank you for the kind introduction, and thank you to the conference organizers for giving me the opportunity to talk about my research. So I started my lab in 2017, and in my lab we built novel neurotechnologies and hope to use them to develop therapies for neurological disorders. Today I'm going to talk about some of those technologies and show the feasibility of using them towards targeted reorganization of the brain. I'm targeting them for stroke, but I want to say that these technologies can be used for other neurological and neuropsychiatric disorders. But let's start with stroke. So as you know, stroke is one of the leading causes of long-term disability in the United States, and current treatments only provide modest benefits. Over the past couple of decades, people have tried neuromodulation as a therapy for stroke, such as magnetic stimulation or electrical stimulation. You might be familiar with the failed Everest clinical trial. I have a photo of their device here, where the goal was to combine epidural cortical stimulation with rehabilitation to accelerate recovery from stroke. However, the results showed that there was no difference between patients who received stimulation and patients who did not, and that led to the failure of that clinical trial. So I actually was involved in this clinical trial as a part of my PhD, and so being involved with that, I think some of the reasons that led to the failure of this trial and to the lack of consensus about the effectiveness of neuromodulation for stroke comes from several factors. The first factor is that in a lot of these studies, stimulation is not specific and affects large regions of the brain. Also, the majority of them are open loop, meaning that the dynamics of neural activity and behavior were not included in generating stimulation protocols. They've been hearing about closed loop neuromodulation a lot since yesterday. And then, most importantly, we don't have a good understanding of the underlying mechanisms of stimulation-induced plasticity. So, optogenetics, as you know, it's a new, relatively new neuromodulation technology that has several advantages over electrical stimulation and magnetic stimulation, and can potentially address these challenges and basically help us open this black box and understand what happens when we stimulate the brain and uncover some of these mechanisms of stimulation-induced plasticity. So really briefly, what are the advantages of optogenetics? One main advantage is cell-type specific manipulation. We can do this with high spatial and temporal control. We can have both inhibition and excitation, so we can do multicolor optogenetics. And we can have artifact-free recording that enables us to understand the direct effects of stimulation. And also, it's important for closed-loop or activity-dependent stimulation. So all of these makes optogenetics a powerful tool to study the brain and its networks. And if we combine that with behavioral capabilities of non-human primates, then we might be able to answer fundamental questions about the brain function or to develop therapies for neurological disorders. So during my postdoc, I developed a large-scale interface for non-human primates for optogenetics by combining 3 technologies. I'm going to give an explanation of each of these technologies. The first technology was a novel viral delivery technique that enabled us to achieve high levels of optogenetic expression across large brain areas. The technique is called convection-enhanced delivery. This is based on pressure gradient. And we co-infused the virus with an MR contrast agent, so we were able to monitor the infusion in an MRI. And as I'm showing here, we had actually very large areas of expression, which was an order of magnitude improvement on the area of expression as well as the time of viral delivery. So the second technology we used was artificial dura. Artificial dura are these clear silicone material that sit on top of the brain and provide optical access to the brain. So the optical access is used for light delivery, right? But we can also use it to image the brain. And so here I'm showing epifluorescent imaging of the fluorescent reporter of the virus that has an in vivo validation of our large-scale optogenetic expression. And the last technology we used was micro-ECOG, or microelectrocorticography array. We designed these arrays to be semi-transparent so they could sit on top of these large expressing areas and provide recording from the underlying network. Because they were semi-transparent, then we could place our fiber optics or light sources anywhere there and stimulate. So a little bit of data from these interfaces. So we implanted them in sensory motor cortex of non-human primates. So M1 is primary motor cortex and S1 is primary somatosensory cortex. These are color-coded based on the areas from 2 monkeys. Each of these blue dots show light illumination. As you can see, we had reliable light evoked responses for both of our monkeys and from both of the areas. We had our animals alive 27 and 29 months post-infusion, and we did not see any decay in light evoked responses, epifluorescent imaging, and of course our histology that I showed you earlier, we had high levels of expression. So to my knowledge, this is the longest lasting and largest implementation of optogenetics in neuroscience, and we published this in 2016, but nobody has beaten us yet. So, but this interface provided a very nice platform for us to ask, now, can we use optogenetics to change connectivity in primate cortex? So we designed our experiments based on the Hebbian learning model, and our stimulation paradigm was very simple. We either had our lasers in M1 or in S1. And then we had blocks of 10 minutes of stimulation that were interleaved with recordings that enabled us to monitor the effects of our stimulation on the network. And we repeated that 5 times, so in total we had 50 minutes of stimulation. So let's see what happened. Here I'm showing functional connectivity maps of the initial baseline of the network. The blue shows the location of stimulation, and these red show, the diameter of these red circles show the strength of connectivity between each of these locations with the location of stimulation. So this is before stimulation. These white circles show the strength of connectivity after stimulation. So as you can see in these 2 examples and across all of our animals and experiments, we see that we were able to significantly strengthen functional connectivity between these 2 areas, between the location of stimulation and the other area. So this was very exciting, right? Because we showed, yes, using optogenetics, we can change functional connectivity. But this is at a large scale, right? This is at a growth level between 2 brain areas. I have about 100 electrodes that I'm recording from these, and if I wanted to see what's happening between each of them, then the result was more complicated. But if you remember, initially I said one of the advantages of optogenetics was that we could record during stimulation. So we tried to see, okay, what's happening when we are optogenetically stimulating? And we generated these maps that each of these enlarged maps is the coherence of that electrode with all of the other electrodes across the array. So basically this map is telling us what is happening during stimulation. And then we generated similar maps on how the network changed after stimulation. And the remarkable result we found is that if you compare these 2 maps together, Or if you compare the general coloring patterns of these large maps, they're very similar. And indeed, we found a linear relationship between them that was consistent across animals and experiments. So this shows that during stimulation, we're forcing the network to fire in this particular way, and it ends up being wired in that way, which is consistent with the Hebbian learning model. But again, remember, this was very simple stimulation paradigm, right? We had one laser either in motor or sensory cortex. And so when we asked that, okay, so what if we have a more complicated pattern of stimulation? What happens then? So we added more lasers, and we varied the delay between the lasers. And to give you an idea is that if I have two lasers and look at what's happening in an electrode between them, you see that, there's this valley due to the first laser, and as it starts to recover, we stimulate. And so we generate this pattern that is different, depending on where your electrode is with respect to these. So that's why it's generating more complicated spatiotemporal patterns. But what we saw was that no matter how complicated our stimulation pattern, as long as we knew what was going on during stimulation, we could predict how the network was changing following stimulation. And so this result was encouraging towards targeted reorganization of the brain. These electrode spacings are about 400 microns. So we could say, we could predict that at that level of, how the brain is changing. But if you tell me that, okay, this is all cool, but if I want to change the brain in this particular way, how should I stimulate the brain, right? So that's the question that my PhD student, Julian Bloch, has been trying to answer. And he's been using machine learning techniques and trying to build models that can explain these changes that we have. So initially, he started building linear models, and his models were getting inputs from network functional connectivity as well as features from our stimulation protocol. And the reason we included network functional connectivity was because, when we were looking at that, so this is the initial network connectivity calculated by coherence, we saw that there's a really good match with the anatomy, right? And so that's what we were using these as the features. And so these are his early models. This is the output of his model and for an example session, and this is the actual change. And so the R-squared of his models was 0.16. It's doing an okay job. I think it's doing a good job in detecting the direction of change. So if you compare that, the increase, decrease, it's doing a good job. But what we were thinking was, most probably these relationships are not linear. And so then we started working with mathematicians and statisticians at UW to try to build models that allow nonlinearity, right? So again, his models had features from the stimulation protocol as well as features from the underlying network functional connectivity. And we did find these nonlinear functions, which I'm not going to go through them, but what I want to highlight here is that, first of all, the R-squared now increased a lot, so now we had a 0.4 R-squared. But the more remarkable result was that the majority of these changes could be predicted by the network, by the underlying functional connectivity of a network in comparison to the stimulation protocol. So to give you an example, this is an example session. If he was only using stimulation protocol, this was his prediction, which is like a poor prediction, as you can see. But if he was combining stimulation with network features, then he could do a much better prediction. And so going back to everything that we've been hearing since yesterday about, state-dependent stimulation, this also shows that even at that scale and talking about plasticity, we need to design our stimulation protocols based on the underlying functional connectivity of the network. So the way I think about it is if we have a stroke patient coming to the clinic, we have to study their brain, and depending on the location and extent of the damage, we have to study that, we have to study their underlying functional connectivity and design our stimulation protocol. But not only that, because we see that these feature mappings change over time. So here we have 5 blocks of stimulation. I'm showing one of the features, which was initial coherence of the network. And as you can see, those mappings change. So it means that as we stimulate the network and as we are changing the network, these relationships change. So again, it means that we have to have these constant updates to our stimulators or our stimulation protocols. Okay, so what I've shown you so far has been on excitatory optogenetics, right? So remember, we had an excitatory opsin that we were activating neurons. But one can ask, can we change the network with inhibition? Because we have inhibition with optogenetics, and if we can combine them, then we can do more complicated patterns of stimulation and changes. So to answer that, as we've been implementing large-scale inhibitory optogenetics, we have also been optimizing our large-scale interface. So I want to take a few minutes and tell you how we have optimized our interface. So we collaborated with Ripple Neuro and printed platinum particles into that artificial dura. So now our artificial dura, which we call multimodal artificial dura, has electrodes in it. And another very cool thing about this technology is that there's no PCBs here, right? So that allows us to store these arms into our chamber when we are not recording. And when we are recording, then we can clamp our PCBs to these arms and record. And so this way we can protect our PCBs. So I mentioned earlier that the transparency of this artificial dura both enables stimulation and imaging. I showed epifluorescent imaging earlier, but we've also showed that in collaboration with Ricky Wang at University of Washington, we showed that we can do optical coherence tomography, angiography, and image blood flow through these. And then the last optimization was that we have built LED arrays that now allow 16 independent locations of stimulation. We build them in different colors, and they're compatible with our interface, so they can sit on top of our multimodal artificial dura and stimulate. So we recently have implanted this in 2 monkeys, and I'm going to show data from 1 monkey only. So as I said, this is now an inhibitory opsin, and again, we have large-scale expression. We are seeing deactivation as we are illuminating. So this is in posterior parietal cortex, which is involved in multisensory integration, and lesions in this area have shown to impact reach and grasp. So in a center outreach task, we are showing that whenever we are illuminating or deactivating PPC, we are increasing the reach time. So this is preliminary behavioral data we're getting with this optogenetic deactivation, which opens up a lot of opportunities for us to see, how all of the rewiring, everything that happens in the brain, how that correlates with behavior. But let's go back to the question that I asked earlier: can we use optogenetic inhibition to change connectivity in the brain? And so our initial preliminary data that shows yes. So during stimulation, we're showing that we're decoupling the location of stimulation from the rest of the network, but that result lasts even after we stop stimulation. So we see some sort of plasticity with optogenetic inhibition. And if you remember from the excitatory optogenetics, I showed that we are strengthening connectivity between the location of stimulation and the network, and this is the opposite effect. And in a way, both of them are consistent with the Hebbian learning model, right, that we said that neurons that fire together, wire together. But the combination of these two can create a lot of opportunities for us towards targeted reorganization of the brain that we can then study functional recovery from injury such as stroke. But I said 2 words here. I said functional recovery, and I said stroke or injury. Everything I've shown so far has been in a healthy, normal brain, right? Ideally, we want to test these in the presence of an injury. And so what we've been working on was to incorporate practical models of stroke into our interface. So this is the technique I'm going to talk about. It's based on the photothrombotic technique. This is a photochemical lesioning technique. So the way it works is that you inject a dye IV, then it will be a light-sensitive dye IV, and then it will be everywhere in bloodstream. And then anywhere you shine light, it can create focal thrombi and focal lesions. So we implemented this in 7 macaques. This is the surface of the brain. We use OCTA to image blood flow, and then inject the dye, illuminated these focal regions, and 4 hours later we image and we show that the blood flow has stopped in these areas that we illuminated. We also validated this from histology. The dye that we use, rose bangle, is pink. So you see that right after perfusion, the dye is trapped here because we damaged the microvasculature there. But we also validated this with Luan and cell staining to show cell death and neuronal death. We have also built a computational model based on tissue optical properties that enables us to estimate the lesion volume beyond the illumination parameters that we have used so that you can plan the extent and depth of your lesion based on this model. And then because our MMAD was semi-transparent, we also did this photochemical lesioning through this, so we were able to record as the lesions were forming. So here, this is the implanted, and so as I said, we could do blood flow imaging, and we could show that now there is a lesion formed. But then I'm showing some neurophysiology here. So this is the baseline in the gamma power, and then this is after stroke. So you can see the areas close to illumination, the activity goes down. So if we categorize them, there are some areas that the activity goes down, some areas that there's no change in activity, and some areas that there's an increased activity. And we see a similar pattern for our second monkey. So if we look at this color coding, and when we try to see what happens in time, you can see that, this is baseline as we start illuminating and forming the lesion. Like everything goes down, but these red electrodes that are close to our lesion, they all stay down after the illumination versus the rest of the network goes back to normal or even does some compensatory mechanism. We can also look at, for example, coherence as a measure of functional connectivity to the rest of the network from that area. And so you can see that we have this baseline, and then as we start illuminating, as the lesion is forming, it starts doing some compensatory mechanism probably, and then it kind of like stays that way, tries to figure out what happened or like why I lost all of my connections. But this is like this is preliminary analysis. We're doing investigations to understand the network dynamics following stroke. But I'm showing it here to give you an idea about what types of data this interface enables us to collect. And so to give you a summary, what I've shown you was the feasibility of large-scale optogenetics, both with excitation and inhibition, the feasibility of changing the network, both strengthening and weakening. We have the capability of inducing lesions with in the same paradigm, and then we can do blood flow imaging. And then we can look at how the microvasculature changes following stroke and as we do our stimulations, and we can combine it with different behaviors from non-human primates. And as you can imagine, the combination of all of this provides a lot of potential for us to explore targeted reorganization of the brain that can be used for stroke, but not only for stroke, but also for a lot of neurological or neuropsychiatric disorders. So with that, I want to thank all of the amazing people in my lab, everyone who helps us with animal care, our collaborators, our funding agencies. I want to say that none of this work would have been possible without the help and cooperation of our monkeys. And then before I end, I also want to say that we have a postdoctoral position opening in my lab for a recently funded R01. And I want to say that not only there's an opportunity to work with all of these cool technologies and study targeted reorganization of the brain towards functional recovery from stroke, but we do have a very fun and welcoming lab. American Heart Association every February has a Wear Red Day, and so that encourages everyone to wear red to raise awareness about heart disease and stroke. So in my lab every year we wear red and we take a heart photo And intentionally, I'm including this here to say this is Seattle in February. So if you are interested, please come talk to me. This is my email, and please spread the word. And thank you so much.
All right. Thank you for this wonderful, wonderful presentation. Who has a question?
There's one hand there.
Hi. So I was wondering about actually timing the stimulation in response to the activity at a particular location. And I was thinking about, for instance, spike timing plasticity mechanisms, where if you change the interval between the activity and when you deliver your stimulation, you could potentially, in a very specific way, either increase or decrease connectivity between those 2 points.
Mm-hmm. Yeah, and so thank you for the question. And usually I have those evoked responses to show you in more detail, but because of the time limitations, I didn't include them here. So whenever we are stimulating any of these areas, motor or sensory cortex, at the site of stimulation we see an evoked response, but we see a delayed response at the other area. So we see a direct response, for example, in motor, and a delayed response in sensory cortex. And the delay that we see is about like 5 milliseconds. So one of the initial ideas of testing to see can we change connectivity in using optogenetics was okay, let's just try single site stimulation and see with this, if I'm stimulating here, keep stimulating in motor, I am evoking activity in sensory 5 milliseconds later. And then that would be consistent with the Hebbian learning model or even spike timing dependent plasticity with that 5 millisecond. And then we saw that there was changes, right? But then we also tried this, and I don't have data here, but we tried to do paired stims, right? So we did stim with short delays according to spike timing dependent plasticity and long delays, right? We did 5 millisecond delays and we did 100 millisecond delays. With the goal, with the hope that 5 millisecond we would see a change between the 2 sites of stimulation and then 100 millisecond not. But then we saw it for some sites, but not all of them. And that was something that with electrical stimulation from the FETS lab also, they're showing that it happens sometimes, but not all the time. And so that was some of the reasons for us to go back and actually study the network and see, and we were thinking that there are other contributing factors rather than just the delay between the locations of stimulation. And so our model actually, the delay is one of the factors that goes to our model, but we have other factors that when you combine all of them, then you can actually predict what is happening in the network. Because a lot of these spike timing dependent plasticity paradigms have been tested in a cell culture that is just very isolated from that complicated network.
Thank you so much. We have one more question. We're running behind a tiny little bit.
Hi, that was a great talk. I also had a question about timing, but my question was, how long after doing the optostim do you see these plastic changes persist? And then also, how long do these constructs continue to express in primates?
So the second question is easier to answer. So we had, for the excitatory optogenetics, this was the C1V1 opsin. We had expression, and we didn't see any change in our expression. This is 27 and 29 months post-infusion. We didn't see any decay in expression in epifluorescent imaging and in, confirmed by epifluorescent imaging and neurophysiology, and of course, histology was just at the end, right? The other question, which is also a really good question, is that how long did they last? So I don't have the answer to that, but how long they last. What I can tell you is that we had these 10-minute blocks of stimulation, and so we started seeing changes after 10 minutes, right? And then after we did 15 minutes, and then we recorded for about another 10, 15 minutes, and we still were seeing the changes. But beyond that, we didn't collect that data. And so that's something that we plan to collect to see how long these changes last. But based on the data that's coming from electrical stimulation, because all of these changes that we have done so far were like arbitrary changes, I think the monkey goes home and they do their own thing, and so that's going to be washed out because they don't need that connection, right? But I think if we have a stroke, if we have a lesion, and then we induce connections that are actually used, right? If we kind of target them towards what has been damaged and then redirect new connections, then they might last longer if they're being used.
Thank you so much. I think we're going to thank Azadeh one more time for this wonderful presentation. All right. It is my absolute pleasure to introduce Dr. Luan, who will be speaking on new advances in flexible electrode technology. She's an assistant professor of electrical and computer engineering in the Neuroengineering Initiative at Rice University. She obtained her PhD at Stanford in experimental physics, followed by a postdoctoral fellowship at Harvard, and then she came to the light and started doing biomedical work. Her work in the biomedical field addresses the interplay of neurovascular coupling and recovery, as well as the use and development of novel ultra-flexible neural electrode types for long-term recording and stimulation. We're so happy to have you. Welcome.
Thank you so much, Ian. The mic is working, right? Yeah. It's absolutely an honor to be here. Thank you very much, the organizers, for inviting me here. And thank you all for staying this late through the symposium. And today I'm going to talk about new advances in ultra-flexible neural electrodes. And we'll be mostly talking about not only using those electrodes to record in the brain, but to do microstimulation in the brain, and also to use them for spinal record. We primarily work with rodent models. A brief introduction of the lab. So my lab works at the intersection between neurotechnology development and their application into neurological disorders. Maybe a half of the lab works on the development and the testing optimization of ultra-flexible electrodes for large-scale intracortical recording, for intraspinal recording, and for making those electrodes for microstimulation. And maybe another half of the lab works on a variety of brain imaging techniques with an emphasis on being able to image cerebral blood flow and microcirculation in the disease model of mini stroke. So we combine electrophysiology and imaging techniques to study how brain reacts and recovers to small ischemic injuries. For this talk, I will not talk about the physiological study of mini stroke at all, and I will be very much focused on the neurotechnology development. For that section of the lab, this is a joint force from my long-term collaborator and partner, Chong Xie, also at Rice, and those are the photos of the two groups together last year and a couple weeks ago when we had a weekend retreat in Galveston Beach. So also those collaborators have made important contributions to the work I'm going to talk about today. I also disclose my financial interest in the electrode technology I described in this talk. We have so many experts about electrophysiological recording sitting in the audience, so I don't have to emphasize how important those electrodes has been to advance both fundamental and translational neuroscience. However, there are a few caveats associated with this electrode being hard electrode implanted in the very soft brain. And one caveat is about the the foreign body response. So this is a histology showing 4 weeks post-implantation of one of those rigid electrodes, you will have this astrocyte scarring tissue encapsulating the implantation site. So what it means for recording is it's basically pushing the neurons away from the recording site, and I think at the same time forming this insulation layer that shield your sensors from the signal it's going to detect. But even if you're not interested in longitudinal long-term measurements of single unit, of high-quality single units, individual neurons, then those electrodes on a much shorter time scale moves relatively to the nervous tissue. This is a beautiful study the NeuroPixel 2.0 put together, and with hundreds of electrodes on a single shank, they can map those drifts that are associated with micromotions between the electrode and the brain. And you see on individual, on clusters of resters, you start to see the units you're holding onto drift between different contacts. But you can imagine if you did not have that many contacts all at once in that region, you will be losing track of which neurons you are actually recording from. So that really happens in a very short, they can happen in a short time duration as well. So flexible implants were developed in the past decades also to mitigate both of these problems. And this is a not inclusive list of the outstanding work about flexible implants that have been out there in the past decades. And you can see there are different but various clever designs and materials and micro devices going in here. But there's one thing common. So they all use flexible substrate that is of a thickness of about 15 microns. And this is the thickness of the neural nexus, the silicon probe as well. If we take a careful look at their tissue probe interface, this is my close collaborator Lauren Frank's work, so I can use this as an example. You can see, and also this is a probe that Neuralink used as well. So you can see, if you look at the tissue probe interface, there is still this clear cut where the probe makes into the tissue, right? And there's the track of the trauma. So we took a different approach. We put the emphasis for engineering extreme flexibility, not on the material for what we use, but on the form factor of the electrode. So in one sentence, we engineer form factors for ultra flexibility. What does that mean? So in practical, from perspective, what we really care about the flexibility in terms of brain implants is not really how soft the material is, but really how deformable the material can be, how easy to bend it, how small the force it is associated with bending that implant, right? If you think about this, the relevant physical quantity is the bending stiffness of a structure, and that is geometrical dependent. So if we take a shank shape at this, the bending stiffness K is proportional to E, which is the Young's modulus, linearly, but it has a much stronger dependence on the form factor of the device, and particularly the thickness, P. It depends on the thickness P to the third order. This means if we were able to reduce the thickness by a factor of 10, we gain 1,000 times in how easy you can deform those electrodes. And this is all the trick we play to turn from flexible electrode to ultra-flexible electrode, as you see there. And that picture is taken in water because the flexibility would not allow freestanding in the air at this moment. And if you look at the device as just fabricated before we release it, there's nothing special. It looks just as the silicon probe, except that we engineered multiple functional layers from insulation to interconnect to the recording site, all within a total thickness of 1 micron. So 1 micron is about 1/100th of the hair of your hair. So within that thin form factor, we pattern the electrode, we make sure the insulation works in vivo, and that's how we get ultra flexibility. So this slide summarizes the ongoing development of those very flexible electrodes we make in the lab. It starts with the first generation that I make with my own hands, and my factory tracks really the work in the lab. But you can see we could pattern this from photolithography. If anyone work on microfabrication, we push further on the resolution of the electrode using e-beam lithography, so we could pattern hundreds of contacts on this 1-micron flexible form factors using e-beam lithography. Still, the take-home message is they're just 1 micron thick. Whoever have worked on animal experiments may already wonder, those electrodes are so flexible, I cannot even take a picture when they are in air. How do I actually send them to the brain, right? Yeah. And by the way, the movie is just the electrode is in the petri dish. If you drop single droplets of water, how much they are perturbed. Yes, we do have to work on implantation method, and we focus on implanting them with as small trauma as possible. So we choose to use rigid shuttle devices that are temporarily attached to the probes, send them to where we want, and retract the implantation shuttle. And there are 2 ways we're doing it in the lab. The first way, and we started doing this, is the sling mechanism. It's just like a needle and a thread. We engineer a micro-sized hole in front of the electrode, and we use a very rigid shuttle device of 10, 20 microns in diameter, either carbon fiber or tungsten microwire. We send the electrode in, we retract the wire. And you can see this, we do it one at a time. It may not be very efficient. Then we develop another method that uses temporary adhesion. So we basically use PEG to temporarily attach those flexible electrodes with shuttle wire, many at once. And then when we implant them in, the tissue fluid will dissolve PEG just in a few minutes, and then we can retract individual wires, leaving the electrode there. So those are the representative recordings we have in rodents. Those are in mice taken in our own lab. And if I were to zoom in on one of those, and this is, we patterned very dense contacts in order to improve the single unit yield. And you can see we're able to resolve nicely formed single units with those electrodes. And in terms of their longitudinal performance, those I show a few animals implants. Typically in rodents, we have high quality recordings from 6 months to a year after implantation. Those are extensively performed in our own labs. We are also beginning to test in non-human primates through collaborations. And also the bottom graph shows the other typical recording evaluation matrix, the unit yield, the amplitude, the biggest amplitude through all the recordings. Okay, so this is kind of my introduction for me. Those are now the new progress. We will have the results for a while. But what I really want to show today is the new progress that we haven't published. We actually did not really have polished the figure. So you will see from now on the figure become maybe the quality of figure downgrades. But I'm super excited for being able to make those electrodes for robust intracortical microstimulation, and also for being able to enable high-quality intraspinal cord recording. So I want to share this very early results with you all. If we have time, I will come down to the large-scale, high-density intracortical recordings. Sorry, I was not looking at my time. Please just let me know. Okay. So let's start with microstimulation. Yes. So when we first developed those electrodes, I'm sorry, I forgot to say, when we developed it, we named it nanoelectronics thread, and with the acronym of NET. So I will just be referring as NET as we go on. So when we first developed NETs, we put a lot of effort into carefully characterize the tissue probe interface. So rather than using the classic histology evaluations, we used in vivo two-photon imaging, and we did longitudinal in vivo two-photon imaging, really tracking the tissue probe interface from implantation to a few months after implantation to hopefully give everyone a full fuller view of how the in vivo brain responds to the implantation. So those are some images we have, and you can see the neurons. The first figure is neurons, and then the second and the third microvasculature. The net labeled as red. Those are all in vivo two-photon imaging in mouse. What you see is really this very tight tissue probe integration. The neurons and the neurites and capillaries really immediately next to net, and net kind of threaded in between the microcapillaries, right? There's no holes, there's no trauma, even when you go in after the initial surgical damage has repaired. So consensus has arisen that the tight tissue probe integration benefits recording efficacy, especially going to long term. But does it have any benefits for microstimulation? So, and this is really in stark contrast with either the rigid probe or other much thicker probes. So the question that we have in mind is, does this tight tissue integration help microstimulation? And we speculate, yes, it does, just from a very simple physical argument. So this means the tighter tissue integration means the neurons are much closer to the probe. And that means you can elicit neuronal activation with a smaller current. That means you have a more focal event because you don't need a bigger one for more spread events, right? And this is a sketch just showing this. And if we do some back on the envelope calculation, this is far from necessary model to capture all the information here, but just back the envelope, you could see if we were able to reduce the average spacing between our stimulation contacts from say 50 microns to 5 microns, we could lead to a drastic decrease of the current needed to induce neuronal activation, and that would mean we would have a much focal effect, much spatially precise stimulation. So then we hope, if this is true, we hope we can drive a paradigm shift from neuromodulation. From the current, what the field has been trying to do is to make the stimulation more robust for large current injection to really improve the tissue probe interface so we can achieve more precise stimulation at a much smaller current that is safer to the tissue, better for the device as well. Okay, but we have more work to do. First, we need to make sure our electrode could stimulate robustly, this requires some engineering work. After a lot of trials, fails, and errors, we settled down with wafer sputtered iridium oxide, and this is our current net for stimulation. We use micro contacts. Each of them is only 24 microns in diameter, and this shows with this, and we made modifications in the fabrication to increase the robustness of the device, and it has been very critical for us to be able to cap the contact layer from delamination. So that makes a huge difference in the stimulation performance. Then we send the device to rigorous in vitro testing, and after 100 million pulses, up to 30 microamp and sometimes higher, we didn't see a degradation of those devices. And for someone who work on in vivo, I always think in vitro tests can only tell you this far. We have to do in vivo tests, and here they are. In mice, we have stimulated those electrodes up to 7 months and about 7 million pulses, and you can see those are the charge injection curves, and they look quite similar right now compared with several months back. Okay. So what are what happens when we stimulate in vivo? So we set up two-photon imaging techniques to visualize the neuronal activation elicited by ICMS in awake animals. And this is because NETS is very flexible, it actually accommodates longitudinal concurrent two-photon imaging very easily. And here shows you our standard animal preparation at the very bottom corner. That's how a chronic cranial window looks. And here is a typical imaging stack. Usually I do not label vessels in GCAM animals, but here it is. So as the movie plays, we're actually taking Z-stacks, so we're going deeper into the tissue. You can again see the tight tissue probe integration. The vasculatures, the neurons are immediately next to the probe. Okay? And we spent some effort to make sure we could tease out the ICMS activation in awake animals from fluctuating spontaneous activities. We make sure we do experiments only on anesthetized animals because anesthesia has unknown effects on neuronal activities. But basically, I can skip the details here, but in the end, we have a high throughput method that allow us to really pin down at any currents, where are the neurons being stimulated and how many there are. And from now on, all the images you see are going to be this maximum intensity projection through from a 3D imaging stack. Okay, then what are the stimulation effects? So first of all, we sweep the current at different and then measure the neuronal response. And this is one of the examples. And you can see at very low current, we have sparse neuronal activation, and then we have more as the current goes on. But if we take a careful look at their spatial span, and this is basically processing the neuronal images into spheres and project this into rings. But you can see, although we did not have a perfect focal effect at low current, lowering the current would make the stimulation effect more local. And we could do this at different stimulation sites and to more get into the biophysics underlying neuronal intracortical microstimulation. But what I want to show is, nevertheless, there is some layer difference when we put multiple animals together, but still, for all layers we look at, if we're able to drop the stimulation current, we're going to have a more focal effect. Okay, and another important thing to understand is stimulation selectivity, meaning if we were to stimulate using two contacts that are very close to each other, are we able to elicit neuronal activation of a different population? And we implant the electrode that only have contacts only 60 microns apart, and we still stimulate one at a time. And this is going through and we do it at multiple currents, of course. And intuitively, what you see is, yes, if I increase the current, I'm going to have more overlap in the population that I activate from those two contacts. And if I make the contact further away, I'm going to decrease the overlap, right? That's all intuitive. But also critically is, how does the stimulation specificity change over time? You can imagine if the tissue probe interface changes, then this very close by contacts, their stimulation effect is going to be changing maybe as the first responder. So that's why we're setting up to test this. Those we basically just repeat the experiment over a time duration of a few months. And we see a very stable stimulation selectivity at 10 microamp. This is actually a high current for us. I will tell you why just in a little bit. So that supports the evidence that we did not have a degrading tissue probe interface longitudinally. Okay, I showed you so many images about neurons being activated, but are they physiologically relevant, right? And to answer this question, we need to set up animal behavior experiments. So here we use water-deprived mice, and we train them through a wheel turning go, no-go task. So basically, if the animal could sense the microstimulation, it's going to turn this wheel passing a threshold, and the stimulation stops, the water-deprived mouse get water rewards. And this is a typical psychometric curve we see as we increase the current. As you can see, we have have high saturation when the current is high, and we have very few premature turnings if the animal is in this no turning period. And we do this at multiple layers. We do this test with stimulating at multiple layers, and the lowest stimulation threshold is always at about layer 5. This is consistent with previous studies from other groups. We also did longitudinal studies, and here it is. We went on to about 200 days after implantation, and we see a very steady decrease of the behavior detection threshold through this measurements. We repeat this on 4 animals, and very consistently, the behavioral detection threshold are all smaller than 10 microamp. And for anyone who work on microstimulation, this is among the lowest threshold people report. So let me replot this graph just in the charge injection, taking into account the pulse duration. So as you can see, our behavioral detection threshold is below 1 nanocoulomb per phase, and often much lower than that. And if I were to summarize this, comparing with some of the representative work in the literature, you could see, and this is the Shannon plot, right? That's K equals 1.85, not really applicable to very small electrodes, but still it shows you where we are. We are very low in terms of the charge per phase and also the charge density, even given we're using an electrode only 24 microns in diameter. And putting this together, I hope this provides the evidence saying if we're able to improve the tissue probe interface, then we could achieve higher resolution, more on-target microstimulation. This is safer to the tissue, have less chance to the device degradation, and good news for the power consumption and battery life, as we just heard as well. So do I still have time, or this is it? 5 minutes. Oh, I have 5 minutes. Okay. So I will try to do in 5. Okay. So the next thing I'm very excited about is we further optimized the electrode to be able to do high quality intraspinal cord recording in mice. And this is a teaser video. This is showing this. For those who work with spinal cord, you would know it's actually notoriously difficult to do in vivo neural recording or imaging in the cord. So from a neural recording perspective, the cord moves a lot. It moves all the time, and it's also very prone to damage. But just the movement itself, the rigid electrode would cause shifts and tissue reactions that is much more severe than in the brain. But also bad news for imaging is the cord and autonomy is very different from the brain, where the white matter is on the outside, the green matter is inside. So it's very difficult to image the cord as well. So as a result, in vivo, like neural activity in vivo in the cord has been such an uncharted territory compared with in the brain. We think the electrode being very flexible would help with the challenges rigid electrode sees, and particularly about not having a lot of strain built up at the tissue electrode interface, and also holding a steady tissue probe interface. So the model, I don't have time to show this, but basically we run a model to calculate the strain energy at rigid electrode, thicker flexible electrode, and 1 micron net, just as we're having now. And we are seeing from the model a 3 order of magnitude dropping in strain energy at where we implant. Okay, and here are and we basically work out the surgical procedures to go into the cord, which is not trivial, but now it works. But here comes the recording. We specifically engineer this type of electrode to have contacts in this zigzag dense packed form in order to increase our single unit yield. And this shows a snapshot of the recording and the units we were able to have. As you can see, we had good spikes, and we have a good isolation score and large amplitude from in vivo recording. Also, if you were able to do these experiments during animal actively moving, so this is just a movie as we're doing the experiments, you can see the animal actively walking, and that does not affect our ability to record individual neurons. We went on to dig a little further, basically use deep lab cut to label the movement of the animal, and then we're trying to see, hey, from the recording, are there correlations? And basically the raster and the red box shows the putative correlation from the neurons we record that correspond with the locomotion of the animal moving. We also set up continuous recording over duration of 21 hours when the animal is just doing whatever it wants to do in its home cage. And then we take the data, we sort them in segments, and we figure out how much movement we have by triangulation. And average on all the units, the graph may not be the most obvious thing to look at, but we're seeing smaller than 2 micron shift between the electrode and the tissue per hour along the shank. And finally, this is preliminary work, but we're able to record single units even weeks, months after implantation, and those shows snapshots of some results. And with that, I think I need to conclude my talk. I will not talk about the large-scale recording, but let me finish with this slide. Like when I started the work in ultra-flexible electrode, I was very much geared towards minimize the tissue damage for long-lasting recording. But as we go deeper into the engineering work, we start to realize the flexible electrode enables other opportunity as well. The miniaturized footprint allows us to do very high-density recording, and the flexibility accommodate tissue motion, which facilitate application in spinal cord or in large animals. And those electrodes are very well suited for concurrent optical imaging that opens doors for multimodal studies with new opportunities. And with that, let me thank the students and the postdocs who actually did the work. So postdoc Roy and Yu are leading the SMS and the spinal cord study, and they are going to hit the job market this fall. So yes, and finally, one advertisement. At RISE, we're building this neuroengineering initiative. Right now, there are 7 of us as the core faculty member. We had a lot of investment from the university, and we're recruiting students, postdocs. So if you're interested, please think about us. And finally, we are going to have our first Neuroengineering Symposium just in 4 weeks. So if you're interested, please join us at Houston. If we are able to have as a wonderful event as this one, we would see that will be a great success for us. So thank you very much.
Thank you so much for this wonderful presentation. All right. Any questions?
Thank you for your great talk. Oh, it's loud, Luan, and really impressive work. I think I missed it, but for the spinal cord, how did you tether the electrode and device and to minimize? I mean, was it still moving? Did you track to see that it was still moving, but then because of the flexibility, it still maintained its position? Is that what happened?
That's right. So we do the same thing in the brain and in the cord. That is to leave a slack between where we implant and where it's permanently fixed. So you can think about it as we have a redundancy in length in this very flexible region that is not in the cord. So then when the cord moves, that part moves, but where we anchor the probe, so there's this slack between the two segments.
Oh, that's great. That's great then, because then it enables, right, that the flexibility relative
That's
to
right.
each other. That's great.
That's
great.
right.
Yeah.
Yeah.
Thank you.
Thank you.
Really nice work. I have some questions about the mechanics of the probes. Do you have any information about like the flexural fatigue of it, and when these are being implanted, how frequent is it that they tear or they break or things like that?
Yeah. That's an extremely good question. I don't have the data. This is something we are actively looking at as well. Yeah. So in the very long-term studies, we do see what we call channel loss. There are electrodes that are good, and then all of a sudden we lose it. It's lost in a way that is not tissue response, because the tissue response would be more gradual, right? But we haven't been able to pin down if this is from the shank tearing or just those connectors that are not meant to, hundreds or thousands times of connecting and disconnecting. So the connectors are a big issue for us. Almost nothing like on the market, on the shelf, meant to this long-term measurement and a lot of connect and disconnect. Yeah, but that's something we're really putting effort into piecing out at this moment. Yeah.
Question. Thank you for the presentation. Considering how small the electrodes are and kind of they probably have very large impedance, can you comment on the instrumentational challenges to kind of acquire the signal from that small size electrodes, and if there are any tricks or anything that you can share with that regard?
So the electrode, the impedance is actually may not be as high as you think. If we do not sputter iridium oxide, if the electrode was just pure gold or platinum, the impedance is about 500 to 800 kilo ohm. And after iridium oxide sputter, the impedance is about 200 kilo ohm. So it's not an issue. Yeah, I'm quoting the numbers at 1 kilohertz.
All right, thank you very much. Let's thank Luan one more time. All right, so let's get to the last speaker in our session. It's my pleasure to introduce our very own Dr. Alex Opitz, who will be speaking on targeted brain oscillations with non-invasive brain stimulation. He's an assistant professor in biomedical engineering at UMN, who got his PhD in theoretical and computational neuroscience at the University of Göttingen, followed by a postdoc in Charlie Schroeder's lab at the Nathan Klein Institute in New York. He studies models and mechanisms of non-invasive brain stimulation such as TMS, tACS, tDCS. Moreover, his interdisciplinary nature has recently brought him to collaborate with animal researchers to use cutting-edge tools to understand the biophysical nature of all of these interventions that I just mentioned. So let's welcome Alex. Thank you so much.
Yeah, thanks so much for having me, and thank you for everyone who's still sticking around at those late hours. So I'm going to talk a little bit about our research here at the UN, like in non-invasive neuromodulation, and those are also my disclosures. And so we're like mostly, so we're really interested in non-invasive neuromodulation, and one of the main reasons of that is that we can immediately do experiments in humans. So we have a very strong translational component. So this talk will kind of span like from basic animal research up to human application in stroke patients. So this is like the one great advantage that we can use that technologies in human participants. And my lab focuses on two main methods, non-invasive brain stimulation, and this using either electric fields or magnetic fields that are applied from outside the head. So non-invasive in that regard means we don't make a hole in a scalp or a skull and implant something, but we apply something on top of the scalp, either electrodes, electromagnetic fields. So just a very quick summary of those methods. I'm sure many of you are very familiar with. One of our main methods that we're studying is transcranial magnetic stimulation. So how does that work? We have a magnetic coil that's somewhere placed somewhere over the brain region of interest that you're trying to stimulate. And then you have a time-varying magnetic field that you create. And the magnetic field is basically just a trick to bring an electric field inside the brain. And so through electromagnetic induction. And those electric fields that we get are quite strong. So they're somewhere on the range of, say, 100 volts per meter. And they can directly, say, depolarize a neuron and cause an action potential. So if I put that over my motor cortex and stimulate strong enough, then can make my finger twitch, for example. That's one of the basic applications. So we have a direct measure output, say like something like a motor evoked potential. And TMS has some like a growing range of FDA-approved indications, with some of most prominent depression, OCD, smoking addiction. Very recent one. It's almost like a growing list, and several new coming in the pipeline. And another technology that we're also studying is called transcranial electric stimulation. So in a way, you can somewhat imagine that as somewhat like the inverse of EEG, electroencephalography. So with EEG, somewhat like measure brain signals with electrodes on the scalp. If you do a transcranial electric stimulation, you kind of invert that. You like apply a current through those electrodes, and somewhat will reach the brain. Those feeds are quite a bit weaker, so like on a range of, say, a sub-volt per meter. So this is way too weak to cause a direct action potential initiation, but still can like modulate brain activity. And this also is a very popular method in human neuroscience research, and with hundreds of ongoing clinical trials today. So, but one thing that always bothered me with those methods a little bit, it's like often a bit of a black box in a way. If you do non-invasive, it's often like hard to measure, say, what's happening inside the brain, right? So we apply some currents on the scalp. And this is a big question, like, where do they go in the brain? What do they do? How strong are those fields? Then we have issues with dosing. That means somewhere like, what are like intensity that we need to create a meaningful physiological response, and so on and so forth. And this is really hard to study, say, in humans, especially with just non-invasive measurements in humans. So, it's really, animal models are just the way to go to study those things. But to kind of start with that, it's not trivial to say, to just use a mouse or a rat or just a non-human primate and then do the same stimulation protocol as we would do in human. This would not relate to a translational stimulation paradigm. And why is that? If you just look at at those images, head and brain sizes differ dramatically across species, right? We have, in human and a gyrated brain, the neurons will have different orientations with respect to those electric fields. We'll have different head size. Head size will determine how strong those fields are. We have different skull, different muscle tissues, and all those things. That will just lead to that the basic stimulation physics will be very different from a human to that particular animal that you're interested in studying that. So before we kind of started doing those research, we kind of were looking at, can you maybe find someone like develop a translation animal protocol just to make sure that someone like the basic physics of stimulation someone like matches what you typically would do in humans to someone like mimic that in an animal model. And so this is a computation modeling study that Ivan Alexeychuk did as a research scientist in my lab, and Some of all these images we typically, what you can show is some of the electric field in volts per meter, so it's color-coded. It's red, somewhat means the strongest electric field, and blue is then like a weak or no electric field. And so this is the electric field inside the brain across a human on the right and a non-human primate and a mouse, not quite on scale, but just to kind of compare that from transcranial electric stimulation. So if you would apply 1 milliamp tACS across those three models, what you see is like a mouse, you will get like a very high field. It's not surprising. You push all this current on all this very small volume, so you get a very strong field. So it's a lot of work that's been done in mouse or rat models. In my opinion, they started more something like ECT than they started like tDCS. But then some non-human primate, you're already quite close to what you would get in humans, so like a factor, say 3 stronger electric fields. But that's something we can very easily control for because it's just the stimulation intensity. We just dial it up a little bit less if we do those research on non-human primates. So it's a really, say, comparable, much more easier to create some like translational protocols in non-human primates. And so now we kind of get to the challenge of, say, measuring neural signals during stimulation. So one method that we electrical stimulation can like use different waveforms, and one method that's where we are very interested in is like using AC waveforms, so like kind of like an oscillating, say 10 hertz stimulation, and then measuring physiological response. And that's some of like the raw signals that you typically get in those recordings. So some like ongoing, some spontaneous neural activity, and then you turn it on, and so you get like some very strong, stimulation artifacts at somewhere on the range of, say, millivolts, while like kind of neurosignal are just in the microvolts. And so people have tried to trying to recover that. The scalp EEG was, more or less a success. And that's also with LFT recordings, you also have the same problem. That's would be very hard, even if it's suppressed at 99%, it's still not quite there. But one thing what you can do is, looking at single units. This is somewhat one of work we did here in collaboration with Luke Johnson here at the U, where we like looking at single unit recordings in macaques with some implanted electrodes somewhere in motor regions. And why like the single unit recordings so good is because you can see here again, like in C, somewhat like our recordings, you see some of those large stimulation artifacts. But so in orange, you see someone like riding those little spikes on top of that. So you see that's a very different waveform and a very different frequency range that you can still like easily extract even while you have some of those strong stimulation artifacts. And so we're able to isolate those single units even in the presence of a stimulation artifact. And so this is great. So let's see what you find. There is some direct physiological response. And so what we did is just basically doing like a basic, say, dose response. We apply stimulation. So stimulation was applied at the scalp level. So there's like mimic the human case or like of a non-invasive stimulation. So not directly on the brain, but like as we do in humans, just having invasive recordings. So we're having just like a rest period and the stimulation period with different intensities and measure single units. And what's also nice is that those artifacts that we call them artifacts, there's actually also a signal, right? And what is that? It's basically just the electric field that's being imposed by the stimulation. So maybe not call it an artifact, it's just the electric signal that comes from the stimulation. So we can use that to just estimate, the electric field that's present during stimulation. So what we did there in Summerfind about the 0.4 millivolt per millimeter electric field for say half a milliamp stimulation. And so this is good that we know that, because we can directly compare that to what we would get in humans. So I had done that during my postdoc, where we measured that what is the electric field from transcranial electric stimulation in humans. And these are recordings in surgical epilepsy patients. So if you undergo epilepsy surgery to identify seizure, a focus, they have those invasive implanted electrodes, and then wait for about a week to develop seizures to identify that, something like a time window to do experiments. And they let us do those experiments and just apply electrical stimulation, say measure what's going on inside the brain. And those measurements you see here is again the electric field in millivolts per millimeter. And what we also found is somewhat about say half a millivolt per millimeter is what you can get with some of us for 1 milliamp stimulation. So human application, you go 1 milliamp, 2 milliamp. Some go even higher, so up to 4 maybe, but so 2 milliamp is somewhere like a very typical intensity use. So with that said, what we do in the monkeys is really compared to what we'll also do in humans. And so let's look at some of the results. So on those plots, so what's color coded is like each of those dots is somewhere like now a spike for action potential. And black is like, say, during the off period, and then in orange is during the stimulation. And so we're looking over oscillation of like a 10 hertz oscillation, so like up and down. And what you see then during stimulation, spikes are more aligned towards, say, here, the peak of the oscillation. And if you do like spike histogram, you see there's somewhere like more spiking happens say during the peak than during, say, like the trough. Like during trough has some suppression of spiking. And so at the left you have like for 0.5 milliamp and then increasing intensity, you see like those say alignment of spiking activity to some bit more pronounced with stimulation intensity. So really showing some like a nice dose response. With high intensity, get more and more stimulation. At the bottom, there was some example from another neuron. And that we did not find in all neurons, but just somewhat like a subset. So it's about 10% of the recorded neurons, we really saw some of the nice entrainment effect. And so, there's a lot of, say, modeling in a way where we're trying to say, how can we understand what's going on? And so we're doing some of those, say, biophysical models in order to understand those, say, stimulation effects better. So how it typically works, a multi-scale model, we do some finite element models to estimate the electric field, and then you have the input to a neuron model. So what does a neuron do in this oscillating electric field research? So like here in the D, you see somewhere like periodic D and hyperpolarization. Some like hyperpolarization, at the bottom, and depolarization at the apical dendrite, and then kind of switching back and forth over time. And what does that hyperpolarization lead to is somewhat that spiking becomes then more likely at certain times when it's more depolarized compared to what's more hyperpolarized. But we have a whole set of different neurons, in our brain. So like, neurons, they have very different shapes, right? You have some of this very, say, elongated pyramidal neuron, or like those more compact, stellate cells, or interneurons. So different types of neurons will react differently to those electric fields. And so in order to also model that is somewhat like just make sure that those models that we have are somewhat also mimic, say, what we know from experimental recording. So one measure is a so-called polarization length. Polarization length is basically a measure of membrane polarization. It's a measure millivolt divided by the applied electric field strength. So this is basically perfectly linear, at least in that intensity range. It's just a more higher field, the more depolarization you have. But what differs across neurons is basically the slope, right? You see that in different colors, depending on what neuron is, will have a higher or lower slope. And in particular, like layer 5 pyramidal neurons are the strongest, but they're the most susceptible to those stimulation feeds. And that's something, we also know for, I guess, many years from something like slice recordings. And so what do this difference in the polarization, what would they do in terms of effects on, say, like then spiking? And so like in our computation model, we basically kind of repeating the same thing we did like, in our in vivo recordings in the monkeys. We just have something like the ongoing spiking activity from these neurons and apply the stimulation and see what happens. And our findings had really matched well what we found experimentally. So we looked at first effects of firing rate as a function of feed strength. And so the stimulation doesn't really affect firing rate. It's just like goes up maybe 1%, 2%. So it's not, they don't fire more. But what differs is somewhat like when they do fire. And that's something you can measure with a phase locking value. That somewhat basically just counts if you do like looking at which phase they fire across a circle, and the more peak those phases would be. And this is something described as phase locking value. And we see again those pyramidal layer 5 pyramidal neurons would have the strongest increase in the phase locking value. And this is also happens already at feed strength, say like about 1 millivolt per millimeter. And this is something would really also fall within the human range. And this is somewhat like, also work that Harry did, a postdoc in the lab. If you want to read more about that, we have just a recent neuroimage paper about that. So the intermediate summary about this transcranial alternating current stimulation, it can already happen at low feed strengths and affects many neurons. And I think the mechanism is basically that we have a change in a spike timing with those applied electric fields, and most likely like large pyramidal neurons are most susceptible to stimulation. And then like this idea of like using brain oscillation for stimulation is something that really fascinates us in the lab. Because many of the stimulation that we apply is just somewhat like in an open loop fashion, it's just like without respect to what's ongoing in the brain. And so, I guess we heard a lot about closed loop stimulation here during the conference. Some of the work we're doing now with transcranial magnetic stimulation, also some of the closed loop stimulation work talk now. So here first, somewhat towards our human research in the lab, so that somewhat, showing what we're doing in the lab. So it's somewhat like measuring EEG and processing that in real time. And then like what we want to do is somewhat like identify the phase of certain brain oscillation, predict something like alpha rhythm or beta rhythm, and identify different phases of stimulation. And so we have built our own closed loop system. And like, for the sake of time, can I go in all the details? But this is a published Journal of Neuroengineering. If you want to read a bit about more. And one thing, this work done by Sina, that was some of his PhD work. What Sina has also developed is somewhat like, say, a robust algorithm, somewhat to predict the next phase of a certain ongoing oscillation. Because we have certain delays, some of us, hardware delays and software delays. So what we don't do is we don't, say, identify right the phase that's happening, but we just basically predict when the next oscillation would occur. And what's special about the work that we are doing is somewhat like using somewhat like a training period where just let the participant do nothing, or just be at rest for a few minutes and somewhat learn more about some of the special EEG signatures and use that knowledge to somehow have a more precise prediction of those ongoing oscillations. So, and then going to some of the physiological results. then it's like seeing, okay, is there an effect of ongoing, say, brain oscillation at the motor cortex on motor excitability? So what does that mean? So we're measuring those motor evoked potentials. You hold the TMS call over motor, let's say left motor cortex, apply stimulation, then you get something called a motor evoked potential. So that you see on the right side, that's basically just an EMG recording, so how strong does like your muscle twitch. And now we apply those TMS at different phases of, say, the ongoing neurodom. So you have some of the motor neurodom, some like 10 hertz range, and apply stimulation at different phases of the neurodom. And then we also looked at the beta rhythm. There's some like another brain rhythm that's involved with motor function. And so those are some of the results. We found this work done by Miles, a postdoc in the lab. So now those bars that basically see is like a motor evoked potential, MEP. So and now we're looking at basically different phases of those oscillations, like the peak, falling edge, the trough, and rising edge. And you see there's a difference depending on when you stimulate. Say at the peak compared to the trough, you get a different motor evoked potential. So it's the idea is your different state of the motor cortex is a bit more excitable, a bit lesser excitable at those different phases, and we deliver stimulation at those different phases. We get a different response. And so our, say, results with the mu rhythm, that's also replicated what the other had already found before. That was good to see. But it was also interesting. So like for beta rhythm, we somehow kind of saw opposite pattern pretty much, where someone like this relationship was reversed. And there's also something we also just have very recently started to try to do that also in chronic stroke patients. So TMS has been explored also for stroke rehabilitation. It's just measuring what's happening during stroke. And first we want to be sure, could a closed loop system even work in stroke, because they have brain damage. Do we get enough of a signal there? But surprisingly it works. We also have a new career award about that, where we say, are we going to make it work for stroke? But now we just saw it actually already works. So that's great. We can see how far we can go. And we've also found those relationships similar to healthy participants in the differences between, say, peak and trough in the mu rhythm. And so, but we also see, so in all those panels from different patients that we record, not every patient has some like the same phase dependency in a way. So it really suggests also the need, depending, on what patient you have, what type of brain damage, you maybe need to apply a different type of stimulation. All right, I don't know how much time I have. Maybe it's a one quick final thing. It's also like the final idea is, so maybe can someone combine those two things, right? You have some of the idea of, say, alternating current stimulation. For me, I always see is it can somewhat impose something like, artificial local field potential in some brain region. So someone push that in a certain brain state in a way to control that and then apply that, apply stimulation then at different phases. And that's something we're also trying to do there, where we say apply now the stimulation. So we have to say 2 stimulation electrodes. So we apply somewhat like a field that would somewhat be aligned, somewhat like lead to depolarizing current at the motor cortex, and then again apply TMS at different phases of stimulation. And so what we found, I think that's like Miles just sent me that like 2 days ago. It was a brand new findings. And again, we found some of this sinusoidal response where we found like a difference, somewhere like between the peak when we apply TMS compared to like the trough. And we again also did say mu rhythm, beta rhythm, but now we found here the exact same phasic response. And it's somewhat like interesting. I mean, now like thinking, why that's the case. But in some ways, it makes sense to me, because like you apply some like this artificial stimulus on it, where we just like in a way override what's going on. and just have some of those, say, deviant hyperpolarization, and that behaves in the same manner. While something like the brain generates those cells with intrinsic mechanism, say alpha, you probably have a completely different ways the brain generates those rhythms than we say like externally apply. But still, as a proof of principle, it's nice to see that if you apply some of those, external stimulation, we can say like modulate motor excitability in similar ways if we would like track that someone in a closed loop fashion. All right, then I guess let me wrap up the whole talk. So it's like if we track and target different brain rhythms, we'll see different physiological responses. So I think that we've clearly demonstrated, and I think there's a real need for real-time, tracking and stimulation. That's something that's only, say, growing somewhat in the TMS field. And but we also saw already that in stroke, this is also the case, that there are also difference in the excitability depending on the phase of the neurorhythm. And so, in a way, what we're trying to interesting or like want to pursue in the future is say whether we can use those methods, say phase-specific TMS and or tACS, as a personalized way for stroke survivors, and also like towards then say plasticity protocols and see whether they can improve functionality in stroke. Then just acknowledge all the students did all the hard work in the lab and the funding agency made that possible. And then also just as another outlook, if you don't have enough of brain stimulation, we have another workshop in June that some of the more focus on non-invasive brain stimulation. Also hybrid meetings will also be live streamed, and also can learn some of those methods also more geared towards students. They have some hands-on and so on. All right, with that I end here and thanks for your attention.
Thank you so much for this wonderful talk. And in June, the weather is actually very, very nice. Do we have any questions?
What were you expecting for a degree of MEP sensitivity to phase in your phase locking work? I saw like a 5% difference there.
Right.
Intuitively, I was expecting a larger effect.
It's like plus minus 5% is basically what we found. But that's basically all just what's like happening at the motor cortex, right? I think there are other factors that will also play a role that will determine, this variability. But so MEPs are very variable, so if you want to, go in the TMS lab and just continuously record those, they will be, sometimes will be very small, sometimes will be huge, so there's just a big intrinsic variability in those signals there, so even, you need a lot of average to get those type of effects.
Thank you. Any other questions? I guess I have one question. So what I always wonder, especially with changing the rhythm of neuronal firing, right, is what is our overarching theory of how this affects behavior in general?
Right. Oh, man.
It's the last question in the last session of the day.
That's why, that's why I do the physics and the physiology at least that I understand a bit better, and that's why I collaborate with you, Jan, to kind of figure that out in future research.
Right, that's a good answer. Let's thank Alex one more time.